Okay, good day to everyone. Hello from wherever you are joining in to Jade Champions Conference. My name is Hanno, and I'm very honored that I get the chance to kick off this virtual conference with you today, whether it's morning, afternoon, or evening from wherever you're watching. We are one big Java family, right? And Java is what unites us. And it doesn't matter where we live or what our preferences are. I would like to talk to you today about concurrency. How concurrency all started in the 90s, how the support of Java for concurrency improved over time, and what is currently happening in Java's latest releases. Now, I actually got the idea for this talk on a Friday night while I was out for drinks with a few friends. And the bar looked something like this, right? We came to this bar and we sat down, and there was a waiter there who asked us, "What can I get you folks to drink today?" And we said, "Well, what do you have in stock today?" And he started listing all these drinks, right? He started creating this entire list. And when he got to like the 20th item or something, we had that feeling. You probably recall it also from your own experience, right? Where you go like, yeah, that sounds good. What was the first thing that you said again, right? The first thing that you said, that sounded good. I quite fancy that today. And we said the exact same thing to this waiter on this particular Friday evening. And the waiter was a bit disgruntled, right? You could see from his facial expression, he was like, why did you make me list all these 20 different drinks when you wanted the first or the second one all along, right? So we had some fun about that. And of course, we made it up to him later that night by ordering more drinks. But while I was there, I was thinking, this is such a good example of the new structured concurrency feature in Java. So I just want you to remember this story because I'll refer back to it later in the talk and try to explain why I thought it was such a good example. I think whenever we talk about concurrency in any programming language, it's very important to talk a bit about the history of the feature and how we used to do things and how we are able to do things right now, today. So I would like to take a little journey with you, right? And I've chosen the train images here because we'll be arriving at different stations, right? Java's concurrency features have been delivered in multiple releases, of course, starting with threads back in the first version of the language. But we've come across multiple train stations, if you will. So during this talk, I will refer to these points as train stations. And I also want to keep referring to this bar and restaurant story that I told you earlier, because it always helps me to pick a very relatable example to be able to understand and grasp a difficult technical concept when you apply it to a very simple and relatable domain. So let's stay with this bar and restaurant domain, right? Well, the restaurant that we are creating today, that we're talking about today, demonstrating Java's concurrency features, is not, the best restaurant in the world, right? In this restaurant, things go wrong on a regular basis. Actually, the restaurant that kind of inspired me to create this talk and all the code examples is the restaurant that is depicted in Sesame Street. Maybe you've watched this as a kid. I know I have. In this restaurant, the waiter Grover always tries to do his best, but never really delivers the food or the drinks that the guests want, right? In this case, a Lego brick. This is probably not what Mr. Johnson ordered in the first place. So let's dive into this restaurant and see how we could model such an example with Java's threads from Java version 1. In this example, I work with an interface called restaurant, and it just has a single method called announce menu. So we can announce a new menu, and it will return a multi-course meal, meaning we are serving a meal that evening with multiple courses, in this case, 3 courses. Well, then if we would program this with threads, we could create a few waiters. We are creating the waiters right here, right? The Sesame Street characters, Grover, Zoe, and Rosita. And we assign them to a thread. We create a few threads, start the threads, 3 threads at the same time. Then we want to wait for all the threads to finish their work, announcing the courses. So we call join 3 times. And then finally, we can get the results from the threads and construct a new multi-course meal. Well, in Java version 1, you would also have to implement this subclass of thread and store the result in the announced course variable. Right, so this is trip down memory lane. This is what you would have to do if you were on Java version 1. Well, you've got a few pros there, because using threads, you can do multiple things at once, right? It is possible in our domain to announce the starter course, the main course, and the dessert course, more or less at the same time. But there are also a few drawbacks. We cannot return a value directly. We have to store it in our subclass of thread. And the second drawback is actually the biggest one, if you ask me, because we have defined a thread, but that is a mechanism or a concept that defines 2 things, actually. It defines the workload, so the work that has to be done, but it also defines the mechanism to run the workload on. It will be this single thread. Well, that's very static, not very dynamic, and it's very difficult to configure. It would be hard, for example, to do the single announcement on multiple threads here, one of the single announcements. Of course, these things have improved in later Java versions, right? If we take our code example that we ended up with threads, and we would start using the ExecutorService interface that was introduced in Java 5, we would end up with code that would probably look like this. And here we see that we can actually configure this ExecutorService to use a fixed number of threads, in this case, 3 separate threads, but we can easily change it here to use a single one or 10 threads or whatever you want. So we have now separated the unit of work, the workload, and the run mechanism. And here we call the announce course method 3 times as a lambda argument to the submit method. And we get futures in return, a future that wraps the return type course. And finally, we would have to call the get method on these futures, which are blocking methods, actually. These will yield the 3 results and allow us to construct a new multi-course meal. Looks good enough, right? We have improved on a few of the drawbacks of the classic thread class. But consider this example for a moment. What if we're sitting down for this nice meal, but in the kitchen, some things go wrong, right? Some ingredients are out of stock, and that means that certain courses cannot be served today. If we would model this by letting the announce course method, this one, to throw an exception every time an ingredient is out of stock and the course cannot be announced, do we then still think that this code is good enough if announce course can throw exceptions? Because there are a few situations that you have to deal with then. For example, here at line 10, if the announcement of the main course by our waiter Zoe takes a long time to execute, right? It's running for a while. But in the meantime, the announcement of the starter course fails because of a missing ingredient, then the entire announce course method will unnecessarily wait for the main course announcement because it blocks on line 13 on main.get. Whereas the sensible thing here would be to cancel the thread that is going to announce the main course, because we already know that the entire result can never be obtained anymore. We might end up with a valid main course, but we already know that the starter course is out of stock today, so we will never be able to construct a valid multi-course meal. Still, with this piece of code, the main.get will block indefinitely until the result is available, and afterwards it will never be used. So that's a shame. There are more problems with this code. If an exception happens in this line of code, announce course, so announcing the main course, then it will eventually be thrown by main.get here on line 13. But if announcing the starter course takes a longer time than the exception that happens on line 10, then this invocation will continue running. It will even continue to run after the entire announce menu method has failed. So we don't have control over our running threads. Essentially, we've got a thread leakage here. And finally, if the code that runs the entire method here, so the entire announce menu method, if that method is interrupted somewhere along the way, then this interruption will not propagate to the subtasks. All the threads that are created here between line 9 and 11 will leak, and they will continue to run even after the entire method announce menu has failed. So ultimately, the problem here is that our program is logically structured with task, subtask relationships, because we need 3 completely assembled courses to return a multi-course meal. But these relationships cannot be expressed in code. They exist in our minds, in the mind of the developer, but not in this piece of code. We would just have to accept that the fact that the ExecutorService interface in Java is based on unstructured concurrency. There's currently no way to apply structure here, or to organize it in a certain kind of hierarchy. So to summarize, I like the fact that the task that we run with ExecutorServices can directly return a value, because it supports callable, the interface that was introduced in Java 5. And the workload and run mechanism have been separated here, but the drawbacks are this approach will wait for all tasks to terminate, even if one of them would fail or is cancelled. This is because of the future, right, that has the blocking get methods. And it also allows for unrestricted patterns of concurrency, because ExecutorService doesn't enforce any task structure. In theory, one thread could create an ExecutorService, a second thread could submit work to it, and the threads that actually execute the work would have no relationship whatsoever to either the first or the second thread. Not sure how old you folks are who are watching today, but I am sure that some of you remember the classic programming language called BASIC, right? And the most famous statement in the BASIC language was the goto statement. That is essentially a one-way jump, right? Go to 0.30, go to 0.70. You jump from one point in your code to another point in your code. And spawning threads from an ExecutorService, like we've done on the previous slides, is essentially like doing one-way jumps with the goto statement in BASIC. They are the concurrent equivalent of that. And that is what I mean when I say ExecutorService allows unrestricted patterns of concurrency. Okay, another concept that I would like to touch upon before diving into the newer features is thread local, which has been in Java since Java 1.2, which it implements a variable that is unique to its own thread. So that means that if you initialize a thread local, then each thread that accesses this thread local variable will have its own independently initialized copy of the variable. And this mechanism is used extensively in modern frameworks to identify a user's request, for example, when they want to store it in a request ID. Using a thread local will make sure that it will be unique for each user, because each user's request is run on a different thread, of course. To give you an example in the restaurant domain again, I've created an announcement ID class that actually ties the announcement that the waiter does to the output that the chef in my code also does. I'll show you the example in a few minutes. But first, let's look at this class for a bit. So this class generates a unique announcement ID local to each thread. It is assigned the first time that announcement ID.get is invoked right here. And it starts off with the value 1. And every time it is accessed, it will call get an increment of the atomic integer there. So in that way, every time a new thread accesses it, it will be increased by 1, incremented by 1. And each thread here holds an implicit reference to a copy of the thread local variable, as long as the thread is alive and the thread local instance is accessible. Only after a thread goes away, so it's terminated, then all the thread local instances are then subject to garbage collection. And this is the way we could use it in our code. So we've got a piece of code from the waiter class here with the announce course method, and it will print some debug output that says, I'm announcing today's starter course or main course or dessert. And there is a certain announcement ID there, right? But the waiter didn't think of this information by him or herself. There's a chef who decides what will be the menu of this day. And the chef class can also call announcement ID.get. And while these methods are executed in the same thread, then this invocation will always yield the same value here. So these lines of code are relevant here. Pros and cons on thread locals. Well, if you want to share such a variable that has to be unique to your current thread, then it avoids cluttering method signatures because it's not necessary to pass them to different methods. You can easily read the same value from both the waiter and the chef class in our example. And it's a very elegant way to bind data that is unique to the current thread. But there are also drawbacks. Again, the thread local variable is always mutable. So any code that can call the get of the thread local is also able to call the set method of that variable at any time. And they have an abundant lifetime in the sense that thread local variables retain their values until they are explicitly removed using their own remove method or until the thread terminates. And when your threads terminate very quickly, like in our example, then it's not much of a risk here. But if threads live longer, then thread locals also live longer in memory. You will probably forget to call remove here. And if these thread locals are present in memory longer, then this can be a security risk because data may unintentionally transfer between tasks. And it can be a memory-intensive approach using thread locals, especially when you use many threads, because thread local variables can be made inheritable, right? So if thread A starts a new thread called thread B, then thread B can access thread A's inheritable thread locals. And the way that Java implemented this is by copying thread locals from thread A to thread B. There's no inheritance or something that can help here. So if you create many threads this way and keep them in memory, then you've got all these little copies of thread local variables floating around in your heap, taking up memory, adding significant memory footprint. Okay, so we've dived deep into the technical stuff already. Probably by this point, you're wondering why does this interest you so much? Well, there's a very clear explanation. At InfoSupport, the place that I work in the Netherlands, we teach a number of courses, and one of them is concurrency in Java. And I always like teaching this course because it is knowledge that you don't need every day, right? But when that day comes, that fateful day that you need, for example, to debug a race condition, then it's very useful to be the one in the room that knows about this stuff. So I really like teaching about it and spreading the news here. And besides teaching this course, it is also very motivating that Java has released a few new features related to concurrency. And I wrote a few articles about when the past new Java versions were released on fuj.io, available for you to read if you want. Overviews, I wanted to say short overviews of the new Java features, but a lot of features have been published in the past few releases, so I didn't manage to get them short articles. Some of them became a bit longer. But there are some stuff about concurrency here as well, so it's fun to follow along, right, and see what's happening in that field. I'm a Java champion, and of course, because of JChampionsConf, I'm also an Oracle Ace Pro. And if you want to keep in touch, my most active social media platform is Blue Sky at the moment, hanno.codes, which is also my website if you want to see what talks I do besides this one. Right. So if you want to keep in touch, reach out to me. I always like that. Okay, now let's dive into the more modern stuff. We've we've laid some groundwork here, some basics. Let's go into the more recent stuff. So if we're still with this analogy of train stations, I would say our current station is virtual threads, right? We've passed the stages of executor service, threads, thread locals, and our current station is virtual thread. Was made final in Java 21, so we are, of course, using this all in production and experimenting with it. Let's do a quick intro of virtual threads if you've never seen it before. So a virtual thread is a lightweight thread implementation that has no explicit mapping to an operating system thread. And it is intended to run only a single task over its entire lifetime. So it should also be short-lived, a virtual thread. The scheduling is then done by the JVM to run on a carrier thread. So with the introduction of virtual threads, the one-on-one mapping that used to exist between a Java thread and an operating system thread has been scrapped, essentially. And every time you create a virtual thread, it is not necessarily true that an operating system thread is created along with it. This is entirely up to the JVM, and you don't really have any control over it if you use virtual threads. Well, that's a lot of text, so let's see this in an image, because images are always a bit clearer, at least that's what I think. So the situation that you see here with the blue circles and the green circles, that is essentially how it used to work with Java's classic threads, right? If you create a thread in your code, it would create such a blue circle, and that would map one-on-one with the green circle, which would be the actual thread in the operating system. And this is also the reason why you cannot create like millions of classic threads, because they have to fit in your memory, and because they have to be coordinated by the operating system. If I recall correctly, every thread has a separate stack, and the default stack size in a JVM is 1 megabyte. So, right, if you have got 8 gigabytes of memory assigned to your Java process, then 8,000 threads, maybe a bit more, will probably be the limit for you. Right, but with virtual threads, this is not the case. Virtual threads has a very different mechanism when it comes to the memory, the stack management. And also, like you see in the image here, you can create multiple of them. Actually, it is quite possible to create millions of them without running out of memory. And I said before that they are intended to run for only a short while, and that the JVM schedules the work onto the platform threads. And that also means that a single platform thread, right, that is now managed by the JVM, can be reused in theory to run work of a second virtual thread after the first virtual thread has finished. So you can actually compare this to virtual memory, right? Virtual threads are like virtual memory. To simulate a lot of memory, an operating system maps a large virtual address space to a limited amount of RAM. And similarly, to simulate a lot of threads, the Java runtime maps a large number of virtual threads to a small number of operating system threads. A classic thread or a platform thread is expensive to create and slow to start and stop. You can compare this to passenger trains in the real world. They can carry a lot of freight or passengers, but they are slow to start and slow to stop. And you can have like tens of them or 20 of them in this image at the same time. By the way, I'm not the one who came up, the first one who came up with this analogy. I have to give credit where credit is due, right? One of the classic books on the subject by Brian Guts also uses trains as a very fitting example. And if trains are the example for a classic thread, what is then a good example for a virtual thread? Well, I think it is like taxis, right? Taxis are cheap to create, well, cheaper than a passenger train at least. They can be fast to start, fast to stop, and you can have a lot of them. Right, and this image is obviously generated by AI because there are a few taxis in the opposite direction here, crashing into each other without actually crashing, but I think you get the point. I couldn't find a regular image that had so many, so I had to resort to using AI here. Okay, so let's get into the major benefit of virtual threads. Why would you use them? Well, when a classic thread performs input-output, like in the sequence diagram, doing a database call, for example, fetching database data, then while it is waiting for database data, it is blocked. It can't do anything, right? It is unnecessarily taking up resources during blocking. The thread cannot perform anything else during that time until the database returns the data, and then it can start doing stuff again. It doesn't have to be a database, it can also be an external service. But you get the point, right? Every time I/O is happening, the thread is blocked. It cannot perform any other work here. When we introduce virtual threads, the situation changes. Like in the previous example, when a virtual thread fetches database data, well, then it still has to block because it has to wait on database data. But the key here is that the virtual thread doesn't exist in the operating system, right? It is a concept that lives in the JVM only. And you can have millions of them. So it is not such a big drawback that the virtual thread is blocked here. If you put the actual carrier threads next to it, so the threads that the virtual thread is run on, what happens then in the operating system is they are only occupied for the time that the virtual thread is actually running something. Once the blocking stage in the virtual thread starts, the carrier thread is freed up, right? Because the logic that controls the blocking and it waits for the database data can be put into the virtual thread entirely. And well, imagine that this piece of processing takes place on the second carrier thread, who doesn't have to be the first one, right? And this piece on the first one again, for example. Well, then you would see that, imagine that we would use a single thread instead of two, and we would merge these green blocks, that all these dashed lines would be the remainder. And that also means that the periods of time where the virtual thread is blocked is actually freed up time, freed up space on the carrier thread. And in theory, in those spaces, different work can run. So virtual threads will not make your code perform faster, but they can offer significantly higher throughput because there is more space to work with here. We don't have these blocking periods anymore. I was at a talk at DevOps Belgium last year in October. The talk was by Gregor Hope, and it was on software architecture, and he said something that I liked. So I put it in my slides. He said, higher throughput means wider bridges, not faster cars. And I do like the analogy here because it helps me to remember when to use virtual threads. Not to make sure that my very CPU-intensive algorithm will perform better, because it probably will not perform better with virtual threads, but to make sure that work can be more efficiently divided when we have a lot of I/O work and a lot of waiting around for users or databases or services to respond to us. So those are the use cases that virtual threads are intended for. And what if we would want to use them in our restaurant domain? Well, with the ExecutorService approach, is quite simple. We would just have to change line 8 to new virtual thread per task executor. And that would mean that this code now runs on virtual threads. And you'll probably notice that the ability to configure the number of threads that we had in the past has now disappeared. And this is deliberate because the idea of virtual threads is that they can perform very small amounts of work and just be disposed of when they're done, because we don't have to go to the operating system to dispose of them. So creating them is very fast, and getting rid of them is also very fast. That also means that the Java language designers don't really want you to create more virtual threads or less virtual threads than is optimal, right? And it doesn't really matter anyway, because for each submit call that I do here, the JVM will probably create a new virtual thread anyway, because it is so cheap to create them. So like I said, millions of threads can run. That means that we don't have to share threads anymore, right? We're probably all used to keeping track of threads in thread pools and reusing them in some way. But we don't have to do that anymore. We can actually assign a new thread to a new user request and have it running while the user request is being processed. And when the processing is done, we can just dispose of the virtual thread and move on to the next request and create new virtual threads for those. Like I said before, platform threads are limited in number because each thread comes with a stack that consumes 1 megabyte of memory by default. But the stack of a virtual thread is not stored in the stack. It is actually stored in Java's heap as stack chunk objects. And because it is stored in Java's heap means it is subject to garbage collection. So the amount of memory that virtual threads take up can grow and shrink based on when garbage collection runs. That is the reason why you can have so many more of them. The fact that you can use a thread per request style with virtual thread also means that you can combine them with the synchronous programming style that Java became famous for. And it also means that a lot of different paradigms like reactive programming, ArcJava or Akka, for example, those frameworks did their best to promote the reactive programming style and making sure that it would run well with platform threads. Well, I would argue that we would have to reconsider using those frameworks now that virtual threads are available, because we probably don't need the features that those libraries have offered us, at least not to make sure that we can program asynchronously in a reactive style. And of course, I've told you this a few times before, creating them and disposing of them is cheap and fast, and they offer better throughput. Virtual threads perform best when running tasks that spend most of their time blocked, right? Because they can benefit from those periods in time where a classic thread would be blocked and wouldn't be able to execute anything. A virtual thread can, in that place, make sure that the actual backing carrier threads are freed up and can process work that is submitted to them by the JVM scheduler that runs on a different virtual thread. This also means that virtual thread will not significantly improve performance when your tasks are CPU heavy, especially when they are long running. So this is the first drawback. They're not really suitable for CPU intensive workloads. And probably they will even add some overhead compared to just running 8 or 12 or 20 platform threads, because there's a bit of overhead with virtual threads involved, right? You have to think about mounting and unmounting, for example. There are tiny bits of code in the JVM here to make sure that a virtual thread is assigned to a carrier thread. And of course, each virtual thread object that is created is subject to garbage collection, so that's also a part of the overhead there. You could also think about the concept of multiplexing, which is the situation where many virtual threads are competing for a smaller pool of platform threads, which will create scheduling overload. And finally, starvation of other virtual threads that are scheduled on the same carrier thread, especially when the active virtual thread is running a long-running CPU-intensive task. Right, so be careful here. Use them for primarily for your IO-heavy tasks. And if you've got very CPU-intensive work, I would advise you to stick with the classic threads for those workloads. Pinned threads is also a drawback because there are two scenarios in which a virtual thread cannot be unmounted from its carrier thread during blocking operations. And this is when it executes code inside a synchronized block or method, or when it executes a native method or a foreign function. Of course, this could harm scalability in the process. The reason that synchronized use relates to this pinning issue is because, as you probably may know, synchronized blocks are implemented by keeping monitors on the locks. And these monitors are currently held by platform threads, not by virtual threads. So that's the reason why in a synchronized block, a virtual thread cannot be unmounted. There are two ways to fix this if you want. You could replace your synchronized blocks with more advanced locking mechanisms like re-entrant locks or perhaps countdown latches, because if you use them, they will not cause the thread pinning. Or you could wait for Java 24 to be released, right? Because Java 24 will have JEP 491, and that is an addition to Java that will fix the problem, because it will change the JVM's implementation of the synchronize keyword so that not only platform threads, but also virtual threads can acquire, hold, and release object monitors, regardless of their carrier threads. But mind you, this will only fix the drawback of pinned threads within synchronized blocks. So when executing a native method or foreign function, the pinning will still be there. And the final drawback of virtual threads, thread local variables do not perform very well with many threads. I mean, virtual threads do support thread locals, but they should not be used to pool costly resources among multiple tasks. I don't think virtual threads should ever be pooled, by the way, because they are intended to run only a single task over their lifetime. But because virtual threads allow you to create so many of them, the memory drawback, the memory consumption drawback of thread local variables will probably be amplified here. Actually, when Project Loom was preparing for the introduction of virtual threads, many thread locals were removed from the java.base module in preparation to reduce memory footprint. And if you are concerned that this is also a problem for your software project, then you could use a system property called jdk.trace virtual thread locals, because it was added for this very purpose. If you set this system property to true, you will get a stack trace every time a virtual thread sets the value of any thread local variable. So you can pinpoint these situations and replace them if you want. Okay, so virtual threads are available now, and we've covered a few drawbacks in the talk up until now, and I'm curious to see what drawbacks will be amplified now that we have got virtual threads available. And I think there are two of them. So like we said, so ExecutorService allows unrestricted patterns of concurrency, right? The one-way jumps that I talked about, just like the goto statement in the basic language. This problem gets worse when more threads are involved, because the unrestricted patterns will become more complicated or, more complex. And secondly, this is the one that I told you just now, the memory intensity of thread locals. When you've got a lot of threads, then thread locals and the inherited thread local values will take up more space, and the memory intensity will increase. So we've been on this train journey, and the current station is virtual threads. Is this then the final station? Well, of course not. These drawbacks that I mentioned are exactly the reason why the concurrency journey for Java is continuing. And that's also the reason why we arrive at two new features, structured concurrency and scoped values. So let's dive into structured concurrency and see what it is about. Let's talk about feature status first. It is currently, we're in Java 23, and it is in third preview. It will be re-previewed in Java 24 next March, without any changes, by the way. So you need to add the enable preview flag to be able to work with it. And let's remind ourselves of the problems we were trying to solve. In this piece of code here, we had a few problems, right? We had thread leakage, and also we couldn't, in a practical way, cancel the threads every time that one of the 3 subtasks would fail, right? Actually, when you think about it, using a single thread would solve a lot of these problems, right? Because in this case, we've announced Elmo, poor Elmo, to be the waiter, and he has to do everything in this restaurant, the single waiter restaurant. And in this case, if the announcement of the starter course fails, then the entire method will throw an exception, and the other 2 announcements will not even take place, right? So we don't have these problems here, obviously, because we're using a single thread. Now, what structured concurrency tries to do is keep the multiple threads, but solve the problems that come with it, right? Just in the way that a single thread would solve it here. So structured concurrency is an approach to concurrent programming that preserves the natural relationship between tasks and subtasks, leading to more readable, maintainable, and reliable concurrent code. And if you've worked on the Go language, you probably recognize this from the Go routines feature. And of course, the Kotlin language has coroutines that also supports structured concurrency. So you could know it from those languages already. To put it into an image, spawning a new thread from an executor service is a one-way jump, like in the picture on the left here. A structured concurrency is a way to turn this to a two-way jump. So there will always be a return call, like is depicted here. And threads in a structured concurrency context will also always run in its own scope, which is the gray area on the right here. They have clear entry points and exit points. All the subtasks must complete before the main task continues. And it doesn't have to be a simple hierarchy. It can also be more complicated like this, as long as each task has clear entry points and exit points. You can actually create a tree of threads here using parent-child relationships. Now, a scope in structured concurrency will continue until all child threads have completed, resulting in a strict nesting of the lifetimes of operations in a way that mirrors their syntactic nesting in the code. So the code will also look like there's a hierarchy. And it also yields a streamlined error and cancellation propagation. So if there's an error in one of the subtasks, it will propagate to the uppermost task, the parent task. And ultimately, this gets you more reliability and observability in your concurrent code. So it derives from the simple principle that if a task splits in concurrent subtasks, they all will return to the same place, which is the task's code block. And I want to show you a little demo of structured concurrency here. So here I've got the exact same code in my IDE, right? And right now my main class is just using the single waiter restaurant. If we run this just to see how it works, then the waiter will always introduce him or herself and talk to the chef to determine the starter course. The chef will then tell the waiter the starter course will be one of a few. In this case, it's carpaccio. And then Elmo will announce the starter course. And he will do the same thing for the main and for the dessert. And of course, the announcement ID is always 1 because we're using a single thread here, right? So let's create a structured concurrency restaurant right now. Create a class. Can't I create this class? That's a shame. Let's do it manually then. There we go. It implements the restaurant interface. That also means that we have to implement these methods here. And we are creating a few waiters. The 3 waiters that we had on the slide, right? And I want these waiters to announce multi-course meals. We are running a structured task scope here. We do this in a try with resources block. And we are using the shutdown on failure constructor here. Let's announce these courses. That means that all the waiters will call announce course, and we will, just like in the executor service example, but in this case, we call the fork method on scope. That means fork a new task, but keep it in the scope so that we can keep track of whatever we have started here. And then we ask the scope to wait for all tasks to finish. We can do that by calling join. And we also want to throw any exceptions if one of those fails. Finally, we can return a new multi-course meal like this. The way this works is when you get to line 22, so line 21 has been executed, then you know for sure that all the tasks have succeeded and that they are finished, right? Because throw if failed will throw the exception. So when you get to line 22, or in this case, line 23, you are sure that you are able to construct a valid multi-course meal here. So that is very elegant. And actually, it is quite visible from the syntactic structure that we are creating 3 tasks here. So let's run the main restaurant. Now we see some different behavior, right? Because we've got 3 waiters now, Rosita, Grover, and Zoe. They're all talking to the chef. We see this announcement ID working here. And we see that desserts, main, and starters have been chosen. Of course, the order is a bit upside down because we're doing multiple threads here. And in this scenario, everything succeeded. So all the announcements have been done. But there is like a course is, I've modeled this that a course needs a few ingredients, and every ingredient has a 5% chance of being out of stock. So if I run this a few more times, probably it will fill within the first 5 or 6 tries, 7. Here we go. So there is an out of stock exception, and the exception says we are completely out of vanilla ice cream. That means we cannot serve dame blanche today. So we cannot serve the dessert. And what do we see? Well, we see that all the chefs are talking. Sorry, all the waiters are talking to the chefs, but no single course is announced. So even though the final course here, through the exception, the work on the other 2 courses that was still in progress is still being canceled. The scope is being shut down because one of them failed, right? And this is something that you cannot get with the other approaches that I told you about. So this is the code that we ended up with. And what we saw is that shutdown on failure shuts down the scope when the first subtask fails, which is also known as the invoke all pattern. There's also the option of shutting down on success. In this case, I have programmed the example that I started the talk with. You're sitting at a bar, the waiter comes to you, says, "What would you like to drink?" And the first waiter, Zoe, start listing beers, wines, and juices. And the second one, Elmo, start listing coffees, teas, cocktails, and distilled drinks. And if there's one drink in these categories that you like, so I've modeled the guest to have a drink preference, for example, cappuccino. When Elmo lists cappuccino here, the guest will say, "I like cappuccino, let's pick that one." And all the other categories, the work that was scheduled to do, will be canceled because we've got a successful result instead of a failing result. I don't have time to demonstrate this example right now, but I'll link the GitHub repository on the final slide. So maybe it's fun to check it out for yourself and see how this code works. So shutdown a success does the opposite. It shuts down the scope, but only when the result succeeds. This pattern is also known as invoke any. And you can actually write your own custom shutdown policies if you want. For example, collect all succeeding results and ignore results that fail, or anything else if you would like. Currently in Java 23 and 24, you create your own shutdown policies by extending the class structure to task scope. But this will probably change in a future Java version. When I have time at the end of the talk, I'll refer to that back. So we've come to the section of the talk that I'd like to call sanity checks, which is one of my favorite sections because it contains a few questions that I can imagine you have after hearing about all this. And the first question is, at least ExecutorService allowed me to pass a thread configuration. Can I still do that with structured concurrency? Well, in a way you can, because, well, the idea is that structured task scope uses virtual threads by default. But you can pass a platform thread factory to an overloaded constructor of structured task scope. So it is possible to pass platform threads, but it is advised you use virtual threads for this. It is a deliberate decision by the Java language designers to not allow thread pools with certain sizes because they feel like structured concurrency performs best with the thread per request approach that virtual threads are so good at. Next sanity check question. Why do we need all these new scope classes? Why didn't they just enhance the ExecutorService interface? Well, the reason for that is that the new classes enforce structure and order upon concurrent operations. So it does not implement the ExecutorService or the executor interface because those interfaces are used in a non-structured way. So they chose not to change the interface because of backwards compatibility. ExecutorServices are used for unstructured code, structured concurrency for structured code. However, I expect it to be straightforward to migrate code that will benefit from structure to use structured task scope. Another question. ExecutorService already supports invoke all, and CompletableFuture offers CompletableFuture.all-off. Why would I still need structured concurrency? Well, this is true. There are some operations there that look like the behavior that we just witnessed, but there are a few differences as well. Invoke all of ExecutorService and CompletableFuture.all-off do not support cancellation. They can only wait until all tasks have finished, whether successfully or exceptionally. creating a task hierarchy and limiting the scope of tasks, that is not possible with the other two approaches. They can also not make the created task return to the same place. They cannot support custom shutdown policies, and they don't use virtual threads by default. However, you can configure, of course, ExecutorServices and CompletableFutures to use them, but they are not used by default. If you're interested in this topic, there's a good article on Medium that I used prior to this talk. You can check out that link if you want. The slides will also be online later if you want. So we've got three similar mechanisms here, and I've put them on a table right here. I don't have time to go through them in much detail, but I'll leave it up on the slide right here. A quick reference of the differences between ExecutorServices, CompletableFutures, and structured concurrency. So when we would be in a physical room, I would say this is the moment to get your phones out, right, and to take pictures of the screen. Or, to refer to the slides back later, that's also possible. Let's summarize. Virtual threads deliver an abundance of threads, and structured concurrency can correctly and robustly coordinate them, and that is why they work together so well. And scoped values is a feature that also works well with structured concurrency, so let's dive into that. These are developed in tandem, right, with structured concurrency, so they are also in third preview. And these are like this is Java's modern answer to thread locals. Let's recap here. Thread locals had some pros, an elegant way to bind data that's unique to the current thread, but they are always mutable, having an unbounded lifetime as long as the thread lives, and they are memory intensive, especially with many threads. Scoped value tries to fix this. They are values unique to a thread that may be safely and efficiently shared to methods without using method parameters. They are immutable, so they can be written once and they can be read multiple times. They are comprehensible in the sense that they have a limited lifetime. And it is already visible from the syntactic structure of code, just like with structured task codes. They are more robust than thread locals. Data shared by a caller can be retrieved only by legitimate callees. And this is what they look like. So you can create a scoped value, in this case called X, by calling scopeDValue.newInstance. And then if you want to pass a scoped value to a piece of code, you call scopeDValue.where, refer to X, bind a value, in this case hello, and then call a run method or a call method, depends on the functional interface of the lambda here. And then within the piece of code here, within the lambda that you pass, hello will be available if you call x.get. This will print hello. So I have tried to use this in my announcement ID. I have added a scoped value on line 2 there, and I've used them in the waiter class announcement ID.get. And the way that I passed the scoped value to the announce method is here, scoped value.where, announcement ID scoped value, announcement ID next ID call, and then within the entire announce method, I can access the scoped value. Yeah, like this. And this is a good one because the waiter method here also calls a method on the chef class pick course. And if we go to that method here, then there I can also call announcement ID.get, and it will get me the same scoped value. But if I would refer to the scoped value outside of this scope here, like before line 4, for example, then I would get an exception. I would run that. So scope values cannot be mutated, but they can be rebound or overwritten, such as in this example. In line 4, we bind hello to the scope value x. That means that for the entire scope of the bar method, x.get will print hello. But on line 9, we rebind the scoped value to hold goodbye for the scope of, well, in this case, the bas method. And here x.get will print goodbye. But when we return to the bar method on line 10 and call x.get, it will print hello again. So it will only be rebound for the scope the nested scope that you define there. And what about inheriting values from its parents? Well, scoped values can be inherited just like thread locals, but there is no copying of a parent's thread scope value bindings, right? So they can refer to each other, so we don't have the memory intensity. And actually, there is a cool feature here on the slide, hidden here, because scoped values in the parent thread, like the one here on line 9, are automatically inherited by child threads that are created with structured concurrency. So this is a feature where the two new features work together, right? The scope value is defined here, and we are calling this piece of code. So for this piece of code, a drink order ID holds the value 1, and also the threads that are spawned here with scope.fork will also have this scoped value available. And this is because, or let's explain it the other way around. If you would try this with a legacy thread management class like ForkJoinPool, for example, they don't support inheritance of scoped values because they cannot guarantee that a child thread forked from a parent thread scope will exit before the parent leaves that scope. It's the same thing with ExecutorService, by the way. But with structured concurrency, this can be guaranteed. It can be guaranteed that all child threads have finished before the parent scope is done. And that is the reason why we can safely use scope value inheriting here, because we can be sure that the values will not be accessed after the scope completes. I think it's very nice to see these two features work together here. Okay, so when should you migrate to scoped values? Are they always a better choice than thread locals or just in certain situations? Well, here's my take on it. I think you should migrate when your thread locals deal with one-way transmission of unchanging data, because then scoped values will be a very good fit. Or if you expect to use many virtual threads, because that will mean that the memory intensity problem will be bigger for you. Don't migrate when your thread local is used in a two-way fashion if you are overwriting it and if you're relying on that behavior, because scope values don't support that. And if you don't expect to use many virtual threads or no virtual threads at all, then the problem of memory intensity is not as big for you, so it might not be feasible to migrate. So to summarize, thread locals don't limit mutability and perform badly with many virtual threads. Scoped values, on the other hand, support immutable values. They come with a strictly defined lifetime, and they can be inherited efficiently through structured concurrency. Okay, so that's very cool to see all these stations and to see what the new features are. What does it mean for me? This is always a question that I like to get asked at the end of the talk. Well, it depends on the way you use Java, of course. If you are a trainer or a developer advocate, you can just get started, right? Try them out, talk about them. I know I'm doing that, so please make sure you do that as well. If you are a developer working on a framework or library, then you can start using the features to enhance your product, right? But be mindful that these features are in preview, right? Virtual thread is the only feature that is finalized. That also means that structured concurrency and scoped values are not permanent parts of the language yet. But we do really need your feedback here, right? Because there are new features and the Java team wants to know how you want to use this and if it works for you or if you've still got some feedback. So make sure to deliver your feedback also to the Java maintainers. If you are a Java developer that works on a Spring application, well, then it is at least possible to use virtual threads in your simple task executors using this method that became available in Spring 6.1. If you are working on a Jakarta EE project, then you are already used to manage resources, and we used to use manage ExecutorServices like the code example at the top. If you would replace it by the definition on the bottom and set the virtual to true right there, your managed ExecutorService will use virtual threads. And it's kind of the same with structured task scopes. You can use the overloaded constructor and pass it a managed thread factory to be able to use threads that are known to the Jakarta EE container. And if you're a Quarkus developer, I've at least found the run on virtual thread annotation that invokes the annotated method on a virtual thread. looks more or less like the suspend functions in Kotlin, by the way. So does it mean that this is our final station, at least? Have we come to journey's end? I don't think any software is done, so also not in this case. But these are the future features that I've read about in the Java enhancement proposal. So firstly, sharing streams of data among threads, sometimes called channels. The JEP says we might propose to do so in the future. No date set or something, no details. So this is something in the distant future, right? And also probably a new cancellation mechanism, also referred to in JEP 4.8.0, but in the distant future. These are future features that are coming sooner to Java because these are confirmed. Synchronized virtual threads without pinning. I talked about this already for a bit. JEP 4.9.1, this was targeted for the JDK 24, so will become available in March, meaning you can safely use virtual threads with synchronized blocks. And improvements to the structured concurrency API. This is not a definitive JEP yet. It is a JEP draft. I've linked it right here. JDK 24 was so full, it will feature 24 JEPs, so the new improvements didn't fit to the release deadline. So I can't promise anything, of course, but it wouldn't surprise me if this would make Java 25 in the autumn of this year. And I just want to show you a quick preview of what the changes are. So this is how we are used to doing structured concurrency with the shutdown on failure constructor right here and the scope.join. These are the changes that would probably end up in JDK 25, right? So I'll switch again. Meaning, so this will be a static method now. You don't have to call the constructor, and the throw if failed has been removed, and the join method will automatically throw any thrown exceptions. And this also avoids using constructors like shutdown on failure or shutdown on success. And this one was changed because previously you had to opt in, right? Call the throw if failed method, and now you just get them, so you can't forget it. The structured task scope.open will by default perform like a shutdown on failure, but you can use an overload of the open method that takes a joiner, and the joiner is quite a flexible interface that determines the policies and outcome of the scope. For example, our bar example shutdown on success would look like this in the future JDK. That takes a joiner here, and the joiner says any successful result or throw. That also means you can plug new joiners here as well. This is also an extensive example here. This is the way to then also pass a thread factory with an overload of the open method as well. And that also means that the JDK in the future will have multiple joiners for you to choose from. That also means that the strategies are, there are more strategies available. So it's no longer a shutdown on failure or shutdown on success, but it can be any successful or throw, all successful or throw, await all successful or throw, or all until. And of course, you can still write your own joiners. Implement the joiner interface. Before we get to questions, I first want to leave you with my final slide. If you want to read about the subject a bit more, the slide deck that you have watched today is available on my website right there. I will probably do a social post on it later today. So if you keep that in mind, keep track of that, then you can also see it there. The GitHub repository is available for you to play around with the code. And here's all my contact information. If you have some more questions later on, I would be happy to talk about the subjects or go through it with you. And with that being said, I would like to thank you for your attention, taking the time with me today to see these exciting new Java features. And if there are any questions, I would be happy to take them.
So, hello, Hanno. This is Michael Redlick. I've been moderating your session the entire time. Sorry for the late start. There was a bit of a glitch, but we got that all resolved. So yeah, so there are some questions and comments. I'm just going to go back to where we were right here. So the first one is a comment from Marianne, and the guys at Netflix had this problem that got deadlocked because of thread pinning due to synchronized blocks, and there was no free platform thread to unblock the other ones.
Right.
So that was, yeah, I don't know if you had anything you wanted to comment on that.
Yeah, well, that is it doesn't surprise me, right? So like I said, in the first version of virtual threads, the object monitors, right, that we rely on to organize locking, took place on platform threads, right? So I think this problem would be fixed quite soon if JDK 24 comes out and they will migrate to that.
Okay, so the next one is from Vincent. He said, virtual threads increase throughput, not speed. Is there possibility in the future in Java threads to increase the speed?
I think we would all like that very much, Vincent. That's a very good idea. But I don't know of any plans, unfortunately. So.
Actually, Marianne had responded to Vincent in which she said that probably not by threads, but maybe using more efficient data structures, like with Project Valhalla.
Right.
So, which is still, I guess, in process of being completed. So.
Yeah, also very exciting.
Yes, absolutely. Okay, so Alessandro asked, what is the main difference between Java virtual threads and Kotlin coroutines in short?
That's a good question. So they are similar, right? They are similar in the way that coroutines are also a way to make sure that running on a thread is not as invasive, right, in terms of memory usage and startup time and disposal time. So they are similar. There are some differences also, because in Kotlin a coroutine is like a first-class citizen in the language, right? And it is also very apparent from the language structure that coroutines exist, because you start up specific scopes and you annotate function with the suspend modifier. That also means that it has to run in a coroutine. So it is clear from the addition of structured concurrency and also virtual threads, by the way, in Java, that it is, I would not say an afterthought, right? But it is an addition to the language, a language that has been in use for almost 30 years already. Whereas in Kotlin, it has been designed this way from the very start. And it also means that they were able to reflect their use of coroutines in their syntax. I know the vision of the Kotlin language designers is that asynchronous code should look almost the same as synchronous code. And the way that they implement coroutines does exactly that. Right, so the language, of course, being it a more modern, newer language, it allows you to incorporate these features in a clearer way, right? With Java, you have to remember which APIs to use. And of course, once you get to know them, you can use them quite well. But in Kotlin, it's more like, it's like you're more immersed into the language. So I think those are the differences.
Awesome. And my good friend Bazlur asked,
Hi, Bazlur.
What do you suggest when we have a mixed type task? There was a case study of Open Liberty, and they decided not to use virtual threads because of that. Any thoughts?
That's an interesting question. I think the only honest answer I give is, of course, the one that you're all dreading, and that is, it depends. I mean, we've heard that answer all too often, right? I think with this case study, I think they did the right thing, right? You would have to see how it performs. Whether it's GPU and IO 50-50, then you would have to see how it performs, and if you see any differences. And when that balance tips to one or the other, then you can make more informed choices, right? But if it's like in the middle, then you would really have to try it out and see if it performs well or not. And of course, the downside is that you already have to do the modifications and take the risk that you have to undo the modifications at the end. But then at least you'll know for sure, right?
Okay. And I think there was maybe a couple more comments. You had a few comments. Thanks for the talk. And I think Simon said at least it might prompt Blaine Getz to write an updated version of his book.
Yeah, that would be cool. I would certainly buy it if he did that.
Absolutely. Yeah, I think that's it. Apologize to everybody for the late start, at this session. So, but of course, it was well worth the wait, and I learned a few things myself at this session. So, thank you, Hanno. Thank you, everybody who has joined in for this session. I know we're 15 minutes late into session number 2, but you can join in at any time. Yeah. And we look forward to seeing you the rest of the conference.
Okay, thank you. Enjoy your day.
Okay. Thanks, folks. Take care.
Take care.